Hello everyone. So today I'm going to talk about application of peridynamics to fracture in solids and granular media. I would really like to thank organizers of this mini symposium for giving me the chance to talk about my work. So here is a quick outline. So in first part we'll look at peridynamics for a continuum solid. I'll give you the overview and show you some theoretical and numerical results and talk about a couple of applications. In the second part we'll jump to PeriDEM model of granular media where again I'll give you the overview and show you some numerical results that will hopefully interest you in our work, then talk about future works. So here is a list of collaborators. So let's look at part 1, peridynamics for continuum solid. So we'll cover the notations first. So x will denote material point, u will give the displacement, z will denote the current coordinate. Similarly, we'll denote another material point by y. S will denote the pairwise strain between y and x. And assuming displacement is much smaller than the size of the domain, we'll work with linearized notion of pairwise strain. That's formula is shown in the right side of the bottom equation. In peridynamics, the internal force is basically sum of pairwise forces. So you have to give a constitutive law that relates pairwise strain to the pairwise force. And simplest example you can think of is a linear spring which has equilibrium length given by the reference distance between point y and x. You can also relate peridynamic force to the more linear elastodynamic force. So assuming you have linear peridynamic force shown in the right side, you can basically say that peridynamic force is equal to divergence of Cauchy stress plus some error where the error is quadratic in horizon. So that model is too simplistic, and if we are interested in modeling fracture, so what you do is you say that when 2 points y and x are stretched beyond critical value as c, you will assume that they are no longer interacting, meaning the force is 0. And you can achieve this functionality simply by introducing this function h shown in orange, which takes 1 when the strain is below critical strain and 0 otherwise. And this is something you can say about peridynamic, that fracture emerged from peridynamic as a result of collection of broken bonds. So before we proceed, let's also look at measure of damage at point x. So we are all familiar with function phi, which takes 0 when none of the bonds in the neighborhood are broken and 1 when all of the bonds are broken. Instead, we'll work with a function z here, which is ratio of maximum bond strain to critical bond strain. And if z is greater than 1, it means that there is at least one bond which is stretched beyond critical value. In all of my plots, I'm basically be plotting function z here. So we briefly looked at PMB model called prototype microelastic brittle model shown in the left hand side. Instead, we'll work with regularized version of PMB, which is we refer to as regularized nonlinear potential. This was first used by Rob in this paper, where he was also able to show convergence of peridynamic to elastodynamics. And in much of our theoretical and numerical results, we are going to use RNP model. So here is a list of governing equations. We have balance of linear momentum, angular momentum, you have boundary conditions and initial conditions. So one of the major contribution of ours in peridynamic is basically in well-posedness and apriori error estimate. So for bond-based model with nonlinear potential and extension of bond-based to state-based model, we have been able to show existence and uniqueness of peridynamic solutions in both Hölder space and Sobolev space. And using that, we have been also able to show convergence of numerical discretization from both piecewise constant and finite element discretizations. So I'm not going to spend too much time on theoretical results, but I'll quickly show them to you. So here is a theorem that shows existence of solutions in Hölder and Sobolev space. Here is a theorem that shows convergence of a piecewise constant approximation when you assume your exact solutions are in Sobolev space. Here is another theorem that shows convergence of finite element approximation when you assume that your solutions are in appropriate Sobolev space. So now let's look at some of the key applications of peridynamics. So one of the nice thing about peridynamic is this. So there is localization of damage. So if you define process zone by the region of points with one or more broken bonds, then basically what it says is that the process zone will shrink to 0 volume or 0 area in 2D as the non-local length scale is going to 0. So there is localization of a region where the damage is seen. This is also something you can say about peridynamics. So peridynamics is a regularization of fracture. So this phrase was used by Rob a couple of times and it took me a while to really grasp the meaning of that. So in simplest term, this is what it means. So discontinuity in displacement along a curved surface is replaced with process zone. In process zone, strains are very high because they're trying to approximate the discontinuity, but bounded. So it means that you can show existence of solution in more regular space than what is possible in LEFM models. So I said there is localization damage, but can we demonstrate it numerically? So here is a setup that does that. So we have a horizontal pre-crack which is going to propagate forward horizontally, And what we are doing is putting the specimen on top and bottom along the vertical direction, and the force is such that average force is independent of horizon, and this allows us to compare the same simulation for 3 different horizons with each other at the same fixed time. So here is a comparison. So in A we have largest horizon, in B we have intermediate horizon, in C we have smallest horizon, and process zone shown in red is thinning down from A to C. And you can do more, you can plot this figure on top of each other at the same fixed time, and when you do that, this is something you get. So process zone of smallest horizon shown in light yellow is contained in the process zone of intermediate horizon shown in dark yellow, and these two are contained in the process zone of largest horizon shown in dark red. And this comes out from peridynamic without having to do too much. Another area where peridynamic really excels is this. So experimentally people measure the wave reflection effect on crack propagation. So the idea is this. So you have horizontal crack which is going to propagate horizontally, and you're pulling your domain on top and bottom edges. It is displacement control. And what you would expect is after quarter of a distance crack has traveled, it will begin to see this wave reflection from top and bottom, and these reflected waves are going to restrict the speed that crack is trying to acquire. And this is something we observe numerically. So we plot the ratio of crack speed to Rayleigh wave speed in the vertical axis, and you can see it is increasing initially, but then it is stabilizing to certain ratio 0.6, and this is something observed experimentally by many people. So peridynamics just gives you that result naturally. Let's jump to the part 2 where we discuss PeriDEM model of granular media. So motivations are basically that existing DM models suffer from many restrictions. One of the thing is the spherical shape particle, rigid body deformation, local features of two contacting surfaces are not accounted for. In certain situations, particle damage can have big consequences on particle dynamics. So objective is to develop high fidelity model that accounts for deformation of individual particles. It can handle any arbitrary shape particles, and it can give accurate contact forces between particles of changing shapes. So we consider peridynamics for intra-particle deformation, and we consider DEM-like contact loss for inter-particle interaction, and we are not pulling this streak out of thin air. So this work is really motivated by work shown in 2 here. So the key idea is that you apply contact between two particles at the local level. So you go to the region where they could have possibly contact shown in A, and you zoom in B, and pick a 2 points Z and Z prime on either side of the particle, and endow this pair of points Z and Z prime by generalized spring dashpot system, where the spring will give you the normal force, dashpot will give you the damping force, and mu will give you the friction force. And this is how you apply contact in this model. So you apply contact locally where there could possibly have contact, and this makes your model, this makes this model independent of shape of a particle. And further, using standard tests like coefficient of restitution and angle of repose test that is typically used in DM community, you can also tune the parameters of this generalized spring dashpot system. For intra-particle deformation, we fall back to state-based model, ceiling state-based model, whose reference is shown here. So one of the customary example that you have to do, test you have to do when you propose new model for granular media is this. So you basically pick a 2 particle and you fix the bottom particle and let the top particle fall freely, and you measure the effect of damping on coefficient of restitution. And as the damping is increasing, you would expect that coefficient of restitution decreases, as we demonstrate in this table. And this also shows the tunability of our model. So you given the coefficient of restitution value, you can tune damping parameters accordingly. So here is a simulation. On left side I have no damping, so it always bounces back to the same height. On middle I have some damping, so every contact it bounces to reduced height, and then the right side I have the different shape and different material properties of the particles. You can also do fractures. You can fix the top bottom particle and let the top particle impact on the bottom particle, and as you increase the impact velocity, you will expect more damage on the top particle. You can also do non-spherical, non-circular particles, and you can do more comprehensive tests. So here we are doing compressive test. So basically we consider 502 circular and hexagon shaped particles, and their radius are distributed using uniform distribution, so they are not constant, and they are horizontally perturbed. Their masses are randomly rotated, so there is no symmetry. And what we are doing is we are letting the top wall move press down on the media at a prescribed speed, and we are going to measure the reaction force on the top wall in the vertical direction as it is moving below. And when you plot that, on x-axis we have wall penetration, on y-axis we have reaction force per unit area along the vertical direction. So you expect that force should grow as wall penetration increases. There could be some small ups and downs, and that is because of the readjustment of the particles. But at the more upper level, it should really grow. But after many of the particles have damaged beyond a recoverable state, that they are not able to restrict the forces that effectively, the media is going to effectively yield, and that is demonstrated in the figure on the left. In figure on the right, I'm plotting the damage. So from T1 to T2, you can clearly see that how the forces are distributed, so force chains. And you can also see from T2, T3, and T4 the increase in damage as we move forward in time. Here is a simulation of the same setup. So I've made this code open source in the hope that larger community will find it useful in their research. I have integrated continuous integration, code quality check, and all those fancy things that you can do in GitHub. I plan to maintain it and further enhance the library. We already have detailed README for someone to get started with the library, and we're working on better documentation. So here's a couple of points where we have our eyes on. So one of the pressing need here is that both contact and intra-particle calculations are non-local, so there is too much of non-local calculation in this model. So we require a more novel methods that can reduce the computational cost drastically. We are also interested in GPU and multi-CPU parallelism, and we are also interested in coupling the model with other physics. And ultimately, we are interested in application of the model to engineering problems where particle damage have a big role. And that is all. Thank you.